And
you know, that would make sense that that it wouldn't be very easy to do H2 because R cross R is not isomorphic to H2. Or is it? No. Yeah, it is.
yeah, R cross R is
No. Wait, see, no, we should be able to do it then. We map it to the negative 1, in that one. So over here, if you map it back over to J squared, we find square root of J, but how would that map over to R cross R?
So the trouble I see with mapping the square root of J, 1, assuming the square root of J exists, by the way.
Well, if you the H2 isomorphism, there you should get a J squared term because what would you call that? I'm just gonna call it.
So you must end up not preserving the defining equation if that mapping to root J, 1 actually does make sense. I'm still not sure if the square root of J exists.
It would be an R cross R because you could rewrite that. You could rewrite it as
very good. So
and we have J and we have J in the 2 by 2 or in the R cross R. And
you would hope that makes sense what you're writing.
Yeah. So this would be what 1 minus 1 to the 1/2. Now you get an I. No.
Right. That's
Can't do it.
now I have a formula for the square root of a hyperbolic number.
What's the formula?
Oh, it's not simple. But
Yeah, but this is stating that you can't.
but you're right. If there was one, it should filter through the isomorphism to R cross R, and it's clear we cannot find a square root of 1 minus 1 R cross R.
So yeah, that claims it's duped. But
I like your idea.
H2
So
complex. Now you do get one.
yeah, so let's write down that map right quick here. So let's see here. I'll call it F again. F from we'll go from C cross H to H4.
H2. What H2? Not H.
And the claim was other way around. No, wait.
It's complex cross H2.
Oh, H2. Yeah, thank you.
We run into some problems because that's a 3 and that's.
Oh, yeah, and I'm sorry. I want the go.
Yeah, flip it around.
I just, for whatever reason, find it much easier to think going from here to there, like that.
And then
The other way, C.
yeah, put C first. I think we run into one.
Yeah, I mean, I think that's kind of less of an adjustment, but so we're thinking F of J is I comma J. Of course, understanding. I mean, if you want me to be J4, J2, this is the kind of thing I'll start adorning them with sub numbers when I've got more than one.
Yeah.
You know, but so more generally, F of A plus BJ plus CJ squared plus CJ cubed DJ cubed.
F1 A11.
Yeah.
Did you start building?
Very good.
Yeah, BF J and then C.
So we square that.
-1 1 And then,
J, right? But-
yeah, oh yeah,
but
J.
yeah.
Yeah, I'm thinking J3 or H3.
And, yeah, so we can write that out. That's A plus BI minus C minus DI, comma, A plus BJ plus C plus DJ. And so when you write it that way, it's kind of like somehow very, very nice in its way.
And now we gotta see how to prove it.
But yeah, I mean, if you're a glutton for punishment, you can try to find the inverse to this, but I mean, you can do it.
Yeah.
So I'm trying to remember how my students discovered a more sort of slick way eventually to understand these isomorphisms. And I feel like I've forgotten some of the technology we discovered, but so yeah, this is anyway, this is in fact, that is in fact the generator of this algebra. And so and that is a generator of that algebra, so and in fact, we've already checked that the fourth power of the image, in fact, maps to 1, which is what's needed for it to actually be an isomorphism. When you go back to the proof that we wrote up.
Yeah.
And so then the next natural question is, setting aside I kind of want to find the inverse for this.
Okay.
But I think you, well, what if you wanted to find the isomorphism to C cross R cross R?
Well, J is equal to the 1 minus 1, so would you get a triple? So you get I 1 minus 1.
Yeah, what was the mapping from H to R cross R? What was that formula? Do you remember?
But I remember J was equal to 1 minus 1.
Yeah, psi of, 1 minus 1, so it was like psi of, let's say A plus BJ for lack of imagination. So A goes to 1 and minus 1.
Yeah.
Oh no, B. So it's plus, so A goes to here and here. And it goes plus B, it goes minus B. I think that was the.
Yeah.
So like that's how to get this copy to that. So all you do is basically compose the F here with psi on the last bit. So you would map this to, A plus BI minus C minus DI. And then, okay, so we do, the A here is A, so we have A plus C plus B plus D. And then A minus B, which is A plus C minus B minus D.
Okay, yeah.
And I believe this to that, let's call it G, gives us an isomorphism of H4 to C cross R cross R.
Yeah.
Now, if that isomorphism is worth its salt, it will map 0 divisors to 0 divisors. All right, so the 0 divisors of like C cross R, they're pretty easy to characterize. It is things of the form C cross 0 cross R. I don't know why I started with that.
And
You could do C cross R, and anything 0 over here. And then, of course, you could have so anything, I mean those, because you can take things of the form, you know, Z 0 T and multiply it by something of the form, you know, W. Well, not W. 0 S 0, and you get 0.
yeah,
So that makes anything of the form zot a zero divisor. It is less obvious, right, what the zero divisors of H4 are.
no, yeah,
However, you can track back,
yeah,
right? So like, you think about it, right? Like, if we have a zero divisor of the form, something of the form 0, you know, A plus C plus B plus D, A plus C minus B minus D, like something of that form. What did that say? I mean, how to get this to be 0? How can we get this to be 0 in such a way that these are not both 0? I don't know the answer, I'm just asking it.
Wait. I think if B and D are equal to each other and A and C are equal to each other.
Yeah, I think you got, so B and D are equal, that cancels.
Yeah.
This guy and that guy cancel. So
Yeah, and that'll give you non.
So A, you should say A equals to C and B equals to D. That ought to do it.
Yeah, because this wouldn't. That wouldn't cancel out. That wouldn't cancel out.
Right. And these are both non-zero?
Yep.
Cool. So, let's see here, tracking back a bit. That means if we have,
You run into a problem if for certain cases like
so you've got like A,
if they're all equal to each other.
so it's A times 1 plus J squared, right?
Mm-hmm.
Plus B times J plus J cubed.
Mm-hmm.
That is the kind of zero divisor in H4 that corresponds to that zero divisor.
You do run into a problem if A is equal to C is equal to B is equal to D. If they're all equal to each other.
If they're all equal to each other and they're non-zero, this is still non-zero.
Oh, yeah.
So it's okay.
Okay.
Now, you might wonder, okay, so wonderful, like, that's supposed to be a zero divisor, but what do you need to multiply this by to get 0, that non-zero thing being 0, right?
Mm-hmm.
So, that should be something where both of these are 0, but this is non-zero, right?
Mm-hmm.
So the null factor, if you will, null factor of alpha needs A plus B plus C plus D equal to 0, and A minus B plus C minus D equal to 0, right?
Yeah.
Yeah, the equations,
Yeah.
right? So that's what?
2A, 2C.
2A equals
0.
2C, so A plus C equal to 0, right?
Yeah.
So, like A equal to minus C.
Yeah.
And what about B and D?
They're being B and D just can't equal.
If we instead of adding the equations, we subtract the equations, we get B plus D equal to 0, right?
Yeah, so that means B minus D.
So instead of, we get like
They're inverses, yeah.
the null factor of alpha, we call it gamma. Something of the form a times 1 minus j squared plus b times j minus j cubed, right?
Mm-hmm.
Supposedly if we multiply, and now the a and the b's don't have to be the same obviously, but alpha times gamma, is alpha times gamma necessarily 0? If I thought through this correctly, it should work out to that.
Well, you get the difference of squares, and then,
I'm gonna call these bars just to,
yeah.
so yeah, AA bar.
Yeah, they're both difference of squares, so they wouldn't be 0.
We get 1 plus j squared times 1 minus j squared, which is 1 minus j to the 4th, right?
Yeah. Oh, it's just 1, that's 0.
And then we also get plus bb bar.
J,
And
J to the 6th.
so you can factor out a j squared,
Yeah.
and you've still got 1 minus j to the 4th. See, because this is
Yeah.
1 plus j squared.
So is that bad, or?
And then what about the cross term? We've got
Oh, yeah.
plus.
J to the 5th.
I guess there's 2 cross terms, right? Plus
Yeah.
a
And B.
b bar, 1 plus j squared, j minus j cubed, and then plus ba bar times j plus j cubed, 1 minus j squared. I think again, in all of these different cases, we can factor out a j. We get the difference of 1 plus j squared times 1 minus j squared, which gives us 1 minus j to the 4th. In all of these, we have 1 minus j to the 4th,
Yeah.
which is 0. And so these alpha and gamma, these are non-zero, non-zero as long as at least a or b is non-zero.
Yeah.
And the product of them is 0. So they're 0 divisors. I'm sure when you go back to the original regular representation, you might be able to see like linear dependence amongst columns or something, given the conditions we have. Maybe, I don't know. But my point to you is just that like this is kind of neat because directly finding 0 divisors in H4 means we've got to calculate the determinant of that and come to terms with it, like through direct algebraic combat. And we could do that. But it's kind of nice to be able to instead
Go to something else.
go to
Come
this
back.
direct product algebra with the 0 divisors are easy to see. Obvious next question. What about H5?
Okay, well, let's see if there's a pattern first. So H2 is R cross R, and then H3 we got complex cross R, and then for H4 we just got H2 or C cross H2. So
Yeah,
R cross R.
R cross R cross C. Yeah.
Okay, so could we do R cross? I want to see if I can find a pattern. So,
R cross R.
yeah.
H3 is C cross R, right? H4. C cross R cross R.
So for H5, we can have R5. We can have
will be R cross H cross C, but that would just be
R cross H cross, yeah.
R.
Yeah,
I guess you could have C cross R.
yeah, and then
R. Sorry.
C,
I'm an idiot.
C cross R.
Mm-hmm. C cross R, yeah, that's another possibility.
Yeah, and H3 says CR, because H3, and that'd be RR, so yeah, CRR. Oh yeah, we could rewrite this as just H3. So yeah, I think those are our choices. And going off the first two, only having one complex thing, I think you should. I would go with the H3 cross H2, but just rewrite it as CR. And then. Yeah,
So you're thinking it's C cross R cross R cross R?
Yeah, and then so we need a J to the fourth, or J to the fifth equal to 1.
Right.
Which. So, A plus BJ plus CJ squared plus DJ cubed plus E J fourth such that J5 is equal to 1. What can we use? J. Here we use IJ. But we're using, so
We need a complex number that has order 5, right?
Yeah, but let's think about it the same way we thought it. And so we first started with the H2 and H3, we started here H2, and then we figured out that you couldn't. You got down to the reals where that real number would screw you over because there's nothing for -1 square root of -1.
Yeah.
But here, we can. That wouldn't screw us over necessarily, because we have a C. And so, to get J to the fifth equal to 1, H3 would, for H3, I got that was E to pi I, or 2 pi. So for this,
And if you think about H4, we use, you know what I is? I is e to the 2 pi I over 4.
yeah. So we could have E. So we need something that fifths to it.
Mm-hmm.
Well, 2 or 3.
Right. We need to solve the equation z to the 5th equal to 1 in the complex numbers. Mm-hmm.
That would work for a complex term.
Yeah, it should be 2 pi I, right?
You're doing 2 pi, 2 pi?
Yeah, 2 pi I. Over 5, I think you have there.
Yeah.
So that number, when you raise it to the 5th power, it gives you back e to 2 pi I, which is 1.
Yeah.
But it's not 1 before then.
But we need an R term or a H2 in our E. No.
Well, if you're going to go with R cross R cross R,
Yeah,
you need
yeah,
R.
one. Yeah. So this would be 1. I need a 1, and
Yeah.
then want to just get ones.
Yeah, just ones.
Yeah.
1, 1. And see that element there, if you raise it to the 5th power, you get 1, 1, 1, 1,
Yeah.
which is the identity in C cross R cross R cross R
Yeah.
cross R. And and yet it's this, the first time its power is to 1 is when it gets the fifth power.
Yeah, and I think you can just keep using that flip. So for this, every time it's an odd number, you change n to the odd number. You just like do.
Yeah, I think you're right. I think the pattern is it's R cross R, and then it becomes C cross R, C cross R cross R,
Yeah.
and then C cross. It's always C cross. You can always write it as C cross as many copies of R as you need.
Yeah, and so we had J2 here, right? And this would just be J4 when it becomes J to the 6th, like H6. Because we need a 1-1, right? I to the 6th is going to be 1. Because,
I would think H6 would be isomorphic to complex numbers cross 4 copies of R.
yes, 4 copies of R.
So
Well, I'm doing this as the 4th, so C cross R, and then R cross R cross R. No, we said H4 was H2, which is R.
H4 was we ended up finding out H4 was
C.
C cross R cross R,
Okay,
or
so
C cross H2 if you like.
yeah, C cross H2. That's right. So H6 would be C cross H4, right?
No.
Yeah, 1, 2, and then 4 here.
But
This would be R.
if that H4 has another copy of C in it though, that would be isomorphic to C cross R cross R.
C cross C cross R cross
Like so.
R. Okay, well then you'd add another. You'd add another e to the 2 pi r, right?
Yeah. So you have, as you said, H2 is R cross R. H3
C cross R.
Yeah, C cross R. H4 is C cross R, which you could write as being isomorphic to C cross H2.
Yeah, sure.
H5 is C cross R cross R cross R.
Or isomorphic to H3, H2.
You could find an isomorphism between, you could take H4, which is this much of it,
Cross R.
cross R, yeah.
Can then do the same thing for H6.
H6 is, yeah, C cross R4, which is isomorphic to, as you pointed out, H5 cross R, yeah.
Yeah, and that should be the pattern from there on out.
Yeah, I don't know if I thought about this before, but yes, Hn plus 1 is isomorphic to Hn. Oh, excuse me, yeah.
-1 cross R.
Hn,
Yeah. Now to prove that,
Cool.
Could you prove that?
Well, yeah, for me, the most like direct proof, I think, is just that Hn Hn is isomorphic to C cross R. How many of them do you need? N minus 2, right?
Yeah.
And then the mapping is just J maps to the jth root of unity,
Yeah.
comma